Okay, I'm going to attempt to go over the answers to your quiz on the cardiovascular system, cardiac function. So for number one, aside from a high VO2 max, what are some of the other physiological signs of a trained aerobic athlete? So for this answer, you could include a lower resting heart rate, a higher resting stroke volume. So cardiac output stays constant at rest, but a trained athlete will have lower heart rate and a higher stroke volume. And that's the same at a given submaximal exercise intensity. So you can say that submaximal heart rate is reduced and submaximal stroke volume is increased in a trained aerobic athlete. Other signs of training are that you have an increased left ventricular end diastolic volume as an athlete, and you would have increased myocardial contractility. You'd also have an increase in the actual mass of the heart, so an increase in myocardial mass. Number two, describe the pattern of change in heart rate and stroke volume as one goes from rest to maximal exercise. So I'm going to do a quick little diagram here. You would have time on the bottom here, or exercise intensity. So as you progress with exercise intensity, your heart rate increases until you get to about maximal exercise, and then it plateaus. So this is heart rate. This is about where you reach VO2 max. But with stroke volume, what happens is you get an increase earlier, and then it plateaus before you get to VO2 max. So again, this is VO2 max, and you get that earlier plateau in stroke volume. For endurance athletes, that might be a little bit different. So endurance athletes might actually have an increase in stroke volume that's parallel with the increase in heart rate. But for most people, you see a linear increase in heart rate until you reach VO2 max, and it plateaus. For stroke volume, it increases at lower exercise intensities and then plateaus before you reach VO2 max. Number three, which ions enter the myocardial tissue during heart contraction and which ions leave? Which ones cause depolarization, which ones cause repolarization? So heart tissue is a little bit different from muscle. So say this is your sarcolemma for muscle. This is the inside of the cell, so the inside of the muscle fiber. And then on this side, I'm going to have the cardiac tissue. So this is outside the cardiac tissue. This is inside. So for both cardiac tissue and muscle, during contraction, first you have sodium that comes in, and that causes depolarization. And then you have potassium that leaves, and that's called repolarization. The difference with cardiac tissue is you not only have sodium that comes in, but you also have calcium that comes in as well. And then you have potassium that leaves. So with cardiac tissue, the sodium and the calcium coming inside cause depolarization, and the potassium leaving causes repolarization. So depolarization means that the membrane potential is becoming more positive as you have these positive ions coming in, and repolarization means it's becoming more negative as you have this positive ion that's leaving. This calcium that comes in to the cardiac tissue causes an increase in calcium release from the sarcoplasmic reticulum in the cardiac tissue. And that's going to bind to troponin, lift tropomyosin off actin, and cause myosin to bind to actin. So the calcium comes in here and it potentiates the calcium release from the sarcoplasmic reticulum. The fourth question here is how does parasympathetic nervous system affect ion channels in the heart, and what effect does parasympathetic nervous system activation have on depolarization? So with the parasympathetic nervous system, you get acetylcholine, which binds to its receptors on heart tissue, and that stimulates the opening of potassium channels. So you get that repolarization, and essentially it's decreased depolarization. So the acetylcholine that's released from the parasympathetic nervous system binds to its receptor. You get opening of potassium channels, and that decreases the amount of depolarization. Number 5, how does increased sympathetic activity affect ion exchange in myocardial tissue? In this case, it increases your sodium and calcium influx and calcium release from the sarcoplasmic reticulum. Number 6, what circa isoform is found in the heart? The answer here is circa 2A. So circa 2A is your slowest type of circa isoform. Recall that the fastest type in your fast twitch skeletal muscle is circa 1. So this is circa 2A, and that is the slower amount of sarcoplasmic reticulum ATPase activity found in the heart. So that's responsible for pumping calcium back into the sarcoplasmic reticulum after contraction. Number 7, which receptors are most affected by endurance training? So those involved with parasympathetic nervous system activation or sympathetic nervous system activation of heart tissue. The answer here is that your beta adrenergic receptors are downgraded with endurance training, and those are the sympathetic nervous system receptors. Number 8, if an individual has an end diastolic volume of 150, an end systolic volume of 30, and heart rate of 190 beats per minute, what is their cardiac output? So for that, you have to use this equation. So it's cardiac output equals stroke volume times heart rate. Your stroke volume is the difference between your end diastolic volume and your end systolic volume. So end diastolic volume is the maximum amount of blood that's going to be in your heart at one point in time. End systolic volume is going to be the amount left over in the heart after a contraction. So the difference is the amount of blood that's pumped out of your heart with one beat, and that's what your stroke volume is. So in this case, we have an end diastolic volume of 150, an end systolic volume of 30. So your stroke volume is going to be equal to 120 in this case. So that's 120 milliliters per beat. When you multiply that by heart rate, you can get your cardiac output. So we'd take 120, multiply it by your heart rate, which was 190 beats per minute. And this is milliliters per beat. The beats cancel out. You end up with milliliters per minute. And your answer should be, ends up being, if you express it in milliliters, I believe it's 22,800 milliliters per minute. Cardiac output is usually expressed in liters per minute, so it's going to be 22.8 liters per minute if you divide that by 1,000. Number 9, how do end systolic volume and end diastolic volume change with increased exercise intensity? So with increased exercise intensity, you're going to have a greater stroke volume. Your end diastolic volume increases because there's more blood coming back to the heart and it's stretching the left ventricle. And then your end systolic volume will decrease. So you're pumping more blood out of the heart with each beat. Your stroke volume is increasing. So end diastolic volume increases, end systolic volume decreases with increased exercise intensity. Number 10, what ion needs to bind to calcium release channels in myocyte sarcoplasmic reticulum before calcium can be released? We kind of covered that in the previous question. The answer here is calcium. So calcium comes into the heart tissue along with sodium, and that calcium that comes into the heart tissue potentiates the release of calcium from the sarcoplasmic reticulum. Number 11, what is the Starling mechanism or Starling's law, and what is the physiological explanation for this mechanism? So this is caused when you get an increased venous return during exercise, so more blood coming back to the heart. You get a stretching of the left ventricle, an increase in of end diastolic volume. This increases your force of contraction. So one of the explanations for the increase in force of contraction and increased stroke volume is with the stretching of the left ventricle, you get more of an optimization of actin-myosin overlap. So actin-myosin exists in heart tissue just like it does in skeletal muscle. And when actin binds with myosin, you get an increased force of contraction. Number 12, why does force output increase to a greater extent for a given calcium concentration when cardiac fibers are lengthened? So this is sort of related to the previous question. So lengthening of the cardiac tissue essentially decreases the cross-sectional area of the sarcomere, and it brings the myosin closer to actin to increase their interaction for a given amount of calcium that binds. So you get a lengthening of the cross-sectional area of the sarcomere. This brings myosin closer to actin, and you get an increase in their interaction, so a greater force production for a given amount of calcium binding to troponin. Number 13, at long muscle lengths in cardiac tissue, is there an increase or decrease in the amount of calcium released from the sarcoplasmic reticulum? The answer here is that there's an increase in the amount of calcium you get released. So you get a greater force of contraction. Number 14, do calcium levels increase or decrease in the cytoplasm of myocytes as heart rate increases? The answer here is that the amount of calcium increases. You have a decreased amount of calcium that leaves the cytoplasm and a greater amount that comes into the cytoplasm. Number 15, which two proteins are phosphorylated to promote relaxation of heart muscle between contractions? The first one is troponin I. So troponin I stands for troponin inhibitory. That troponin helps to place tropomyosin over actin and prevent myosin from binding with actin. So that promotes relaxation. The other protein is phospholamban. When phospholamban is phosphorylated, it inhibits, decreases the inhibition of your SERCA enzyme. So that allows for more calcium to be pumped into the sarcoplasmic reticulum and promotes relaxation of the heart tissue. So the two proteins that are phosphorylated are troponin I and phospholamban. 16, What protein is phosphorylated to increase calcium release from the sarcoplasmic reticulum in myocytes? So the answer here is your ryanodine receptors or your calcium release channels. So your ryanodine receptors are the same thing as your calcium release channels. So this responds to the calcium that comes in. This is calcium stimulated calcium release. So it's the phosphorylation of these channels that causes greater calcium release. Number 17, what accounts for most of the increase in VO2 max of VO2 or oxygen consumption of the heart muscle. So is it delivery of blood through coronary arteries or increased extraction of oxygen from the blood? So it's the level of enzymes and capillarization in the heart tissue that determine the extraction of oxygen from blood, but those are already very high in heart tissue. So you don't get too much of an increase in VO2 from extraction of oxygen from the blood. So the increase in VO2 in the heart muscle is mainly due to an increase in delivery of blood through the coronary arteries. Number 18, what is the simple non-invasive method to measure the amount of cardiac work during exercise? And I gave this answer away, I think, during last class. This is referred to as the rate pressure product. Rate pressure product. And this is equal to your systolic blood pressure multiplied by your heart rate. So that can be easily measured during exercise, and that can give you an indication of how hard your heart is working and your myocardial oxygen consumption. Number 19, what two metabolic pathways are stimulated by calcium influx that allows ATP production to match to ATP breakdown in the heart muscle? The answer here are, your two main aerobic metabolic pathways. It would be the tricarboxylic acid cycle, also known as the Krebs cycle, and the electron transport chain. So it's your Krebs cycle or TCA cycle and the electron transport chain. Number 20, what tissue has the greater percentage increase in myocardial enzymes with endurance training, heart or skeletal muscle? So heart muscle already has a very high level of mitochondrial enzymes, so there's very little room for improvement with endurance training. Whereas your skeletal muscle, if it's very sedentary, your mitochondrial enzyme level can go very low. And with intense training, you can increase your mitochondrial enzymes to quite a high level. So going from being a couch potato to being very highly aerobically trained, you can increase your mitochondrial enzymes in your skeletal muscle by 1 to 2 times, so almost like 200%. So the answer here is skeletal muscle. Number 21, what accounts for the larger left ventricular size with endurance training at the cellular level? And how does this differ from the cellular changes you see with hypertension? So this is what's referred to, first of all, with endurance training. You get what's called eccentric hypertrophy. So what's happening at the cellular level is you're getting a stretching of the left ventricle. So within the left ventricular wall, you have sarcomeres that are made up of actin and myosin myofilaments. So I'm going to just draw, say, a sarcomere here. This refers to your myosin, and this is your actin. And for contraction to occur, for the heart to push out blood, you need myosin to bind with actin. and that increases the force of contraction of the heart muscle. With eccentric hypertrophy, you get addition of these sarcomeres end to end as you get a stretching of the left ventricle. So you get sarcomeres increasing this way. So this is going from before to after endurance training. You get this eccentric hypertrophy. This is also referred to as an increase in sarcomeres in series. So with hypertension and also with a lot of resistance training, you get a thickening of the left ventricle. So what happens to these sarcomeres is they will instead increase in parallel. So say you had just a couple of sarcomeres here. This is before training. What would happen, or before strength training or before hypertension, what happens with hypertension or strength training is these will increase in parallel. They'll increase this way. So your heart tissue is actually becoming thicker. Just like your muscle, your skeletal muscle becomes thicker and hypertrophied this way with strength training. So this is called an increase in sarcomeres in parallel. So increase of sarcomeres in parallel. With hypertension, you get this effect, and it negatively affects heart function. With strength training, you get the same effect, but you don't get the same negative impact on heart function. And the last question is, what changes occur with endurance training to allow the heart to receive a greater supply of oxygen? And the answer here is that you get an increase in the vasculature of the heart. So an increased branching of the coronary arteries. So the coronary arteries are those arteries that originate at the aorta, and they're responsible for delivering blood and oxygen to the actual heart muscle tissue. And that's it for your quiz on cardiac function.